Okay, in this video we'll talk finally about what makes something a good nucleophile, and we'll expand a little bit on, what at least what some typically good leaving groups are. We've already kind of said that leaving groups are weak bases, but we'll take a look at what some common ones are. So let's start our talk. Let's start our talk here with, let's just look at leaving groups because we've already kind of talked a little bit about that. So leaving groups, when we're looking at these reactions, we have a nucleophile that's coming in. This could be SN1 or SN2, it doesn't matter. But the leaving group is essentially whatever you're getting rid of and replacing with the nucleophile. So typically your leaving group will have a negative charge. We'll see some examples where that's not true, but this is kind of what we're looking at. But so if you want to kind of figure out how good a leaving group is, we want to use a similar logic to what we used in our acid-base chemistry chapter, where we're not looking at the bond itself, we're looking at the product. So in acid and base chemistry, instead of looking at the strength, when we were trying to figure out the strength of the acid, we would look at its conjugate base, which is the product of the reaction with the acid. And reactions and products, if you think about it from a thermodynamic perspective, you're kind of, these, I guess they're interrelated. It's kind of like looking at different sides of the same coin. So the logic can get a little bit confusing. But if you kind of look at it at a fundamental level, it should hopefully make sense. But yeah, if we're looking at all of these different substrates that I've drawn here, we can consider what the leaving group is going to be. Leaving groups are never, ever, you're never going to have just like a hydrogen leaving group, or a carbon that's going to leave or something like that. It's almost always going to be some sort of heteroatom, or some sort of like fancy carbon functional group, which is less common but can happen. But yeah, if we wanted to consider which of these were the best, how good these leaving groups are, you could kind of just consider in your mind what it would look like after it leaves. So what's this one going to look like after it leaves? It's going to form Br minus. This one's going to form I minus. This one's going to form OH minus. And this one's going to form NH2 minus. And so if we're trying to rank which of these are the best leaving groups, all you have to do is rank them in terms of their basicity. So we know that this is a strong base. This is an even stronger base. And we know that these two are very weak bases. So if we're trying to rank these absolutely, we would say, well, I minus, that's going to be a better leaving group than Br minus, which will be a much better leaving group than OH minus, which will be a much better group, if not much better leaving group than NH2 minus. Okay, so it's normal to see these as leaving groups. Once you start to get to things that are at least as strong as OH or stronger in terms of basicity, so I'm talking about pKa's here, so if the conjugate acid of the base has a pK of above 14, you're typically not going to see that as a leaving group. So when the pKa of the conjugate acid is above 14, it's usually not a good leaving group. And the reason for that is, if we're thinking in terms of stability or reactivity, you're not going to, typically when you do a chemical reaction, you don't start with, you don't generate something that's more reactive than what you started with, if that makes any sense. It's just like, it's a simplified way of saying that, like, you don't do things that are thermodynamically uphill. If you look at this in terms of equilibrium, things of that nature, you can kind of calculate why that's true. But it should make sense intuitively that just you generally don't go from something that's low energy to something that's really, really, really high energy. And that's really what we're talking about when we're using fancy words like exergonic or exothermic and stuff like that. And that's kind of what this statement gets at. It's just that, yeah, if we're not going to form a really strong base in a reaction, we're not going to take a weak base and exchange it for something that's a strong base, because you're making this, you're going from something that's not reactive to something that's really reactive, and we kind of just don't see that. Okay, so our leaving groups, you really just use your acid-base chemistry to decide whether something is a good leaving group. The halides are very common leaving groups. So let's see if I have a list here somewhere maybe. Yeah, the halides are really common leaving groups. The other leaving group that's a little weirder for you guys is the tosylate group, and I cover that in a different video, but I'll show right here. And then I'll show you how you can have water be a leaving group, which is a good leaving group. Yeah, it doesn't look like I have a complete list, and it's hard to draw a complete list. So I guess what I would say is a blanket statement, any weak base can be a good leaving group. So yeah, so some common leaving groups that don't require any finesse to them, no extra reaction steps. I'll show you some ones that you can, some tricky ones that are a little bit trickier that involve proton transfers, would be things like I minus, Br minus, Cl minus is a good leaving group. Let's see, what's another good leaving group? So the weird one is tosylate, weird one for you guys at least. This is a good leaving group. Sometimes you'll see this abbreviated as this. We'll talk about, eventually get to kind of like what that group is and why it sort of has special significance. But for you guys, you can just kind of think of this as being the conjugate base of sulfuric acid. So this we can kind of think about being the conjugate base of sulfuric acid. So it's a really weak base, even though it's something you probably haven't seen before. Yeah, I think those are most of the really, really common leaving groups. It's not the only ones. You can get other things to leave, but those are some of the common ones, and we can always come back and add to that list. Okay, so these are just ones to watch out for. And so these are ones where you don't have any kind of proton transfer or anything. We're going to get to that. Nucleophiles, unlike leaving groups, are much trickier. So leaving groups, if it's a weak base, it's a good leaving group. That's always true. And so this statement right here is one of the few things where I feel like I can stand by it in organic chemistry and say there's really not a whole lot of exceptions to this. If you've got something that's a weak base, it's going to be a leaving group, good leaving group. Nucleophiles, trying to figure out why one is better than the other. We can rationalize it, but it ends up getting to be like the number of ways you have to use to rationalize it to try and find a pattern just ends up not being super, super useful. It's easier just to memorize the damn things. But you can see some patterns, and I'll point those out. But in general, unfortunately, you just kind of have to memorize what are good and what are bad. So what are good nucleophiles? So you'll see right here, all right, that's a good nucleophile. And if you look back at that alkylation reaction that I taught you, where you take acetyl anion, you'll realize that what you're doing there really is an SN2 nucleophilic substitution. So you've already had some exposure to this reaction, you just didn't have a name for it. So all of these are pretty good nucleophiles, and you don't really need to know the ranking of them, But you'll notice that in many cases, the nucleophiles, good nucleophiles, are also strong bases. Right? So strong bases are usually good nucleophiles. There's one exception to that. But just because something's a weak base doesn't mean it won't be a good nucleophile. And we see that right here. Both of these are extremely weak bases, but they're still good nucleophiles. And so explaining that can, it's complicated, but I think the main thing to take away from here is that like nucleophiles themselves are just kind of complicated. It's harder to say what a good nucleophile is than what a good leaving group is, right? So we could talk about polarizability and why that makes bromide and iodide good for nucleophilic substitution or good nucleophiles. But I think that's beyond the scope of what you really need to know at this point. Moderate nucleophiles are these. And then just straight up bad nucleophiles, things that are not super reactive as nucleophiles, are these. So a couple of things you can note here is, I'm not sure if I have enough colors to do all these, but if I look at an acid and compare it to its conjugate base, the conjugate base is almost always a better nucleophile than the acid would be. And this makes sense because nucleophiles we know are electron-rich species, and deprotonating them puts more electrons on them. Another example of that might be, if you look at this is a moderate nucleophile, but if I deprotonate it, now it's a good nucleophile. If we look at the conjugate acid of bromide and iodide, they're not nucleophilic at all. And then let's see, what's another? This is a good nucleophile, but if we come down here and look at this, it's a bad nucleophile. Water would be kind of in the same spot there, right? OH minus would be a good nucleophile, but H2O is a bad nucleophile. So there's some patterns there, but they're kind of hard to see. There's another one over here. If we look at this, it's a moderate nucleophile, but if we deprotonate it and look at something like that, yeah, now we've got a good nucleophile. Okay? So that's really the main thing is like if you deprotonate something and put a negative charge on it, generally you're making it a better base, so that means that you're making it a better nucleophile. But as far as kind of being able to predict kind of this nucleophilic trend that we're seeing here, how the nucleophilicity decreases as you go down, yeah, I mean, there's some stuff that you might be able to look at and say makes sense, but generally it's kind of hard to do that, I think. I think more the way that we know these are good and bad nucleophiles is that they've just been studied in reactions, and and you can say based on how well these things react, this is a good or bad nucleophile. And then we can kind of back rationalize, but kind of trying to go forward with it and draw any kind of real conclusions about patterns like we did with acids and bases, I think it's just much harder to do and just not super useful for us. Yeah, so those are our nucleophiles. I would recommend just straight memorizing these. There's 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 14 of them. Many of them are just conjugate acid-base pairs, so you don't really have to memorize both of those. You can just, well, I guess you have to memorize the order of them, but it makes it a little bit easier. But I would just memorize these. There's really no reason not to. Of course, our quizzes right now, because we're online, are open book. So if you don't want to spend time memorizing them, obviously I have no way to test you on that, but at least put them on flashcards or something so you have them around for the second course. And if you work enough problems, you'll get familiar enough with them to where it won't be. It's not like you're going to be like haunted by not having memorized these for this course. You definitely just want to be familiar with being able to recognize a good and bad nucleophile. At the very least, I would say you can memorize the bad nucleophiles. There's only 3 of them, okay? And that alone has some predictive value. Everything else, if you can identify it as a nucleophile, is at least moderate or good, okay? So at least memorize the bad ones. You notice all of the bad ones don't have a charge, right? None of the bad ones are negatively charged. So yeah. Yeah, do I have this series like strictly memorized even in my mind? Yeah, I kind of know most of them, but even so, I don't have it like down. Like if you were like, explain to me how much better cyanide is as a nucleophile than like, I don't know, NH2 minus, I'd have trouble kind of telling you the major, with the biggest, how big of a rate difference or something you're going to see there. So it's not going to be like crucial for the course, but you do have to be able to identify these things. So, okay. So these are the standard nucleophiles. Those other ones are the standard leaving groups. Let's take a look at the situation where you have, so remember I said, generally this is going to be a bad nucleophile. So let's say you had this reaction set up. Let's say I wanted to do this. I'm going to take iodide, which I now know is a good nucleophile, and I have, what color am I using? Orange. And I have OH, which we know is a bad leaving group. It's got this great nucleophile, right? But I have a bad leaving group. So people wonder, like, well, maybe iodide is such a good leaving group that it just doesn't matter, and it can displace OH minus. So this would be SN2. You don't know how to predict that yet, but that's okay. I'm just telling you. So this would come in and kick this off. This is the hope, at least, if you're setting this reaction up. Oops. You would form this. That would be kind of the hope here, right, if you're doing this reaction. So now the iodide is connected. The OH minus has popped off. Okay, this doesn't happen, though. So regardless of how good the nucleophile is, if you have a bad leaving group, which this is a bad leaving group, you're just not going to get a reaction. So you'll never see this. This doesn't happen. Okay. Before I kind of scratch this out, just so to make that really, really clear, I'll outline it in red. So this doesn't happen. Okay, this reaction just doesn't go. But why doesn't it go? The reason is kind of what I was talking about earlier. If you just think about the thermodynamics just from an acid-base perspective, right? Here I have a very weak base. And we can think about kind of how we talked about equilibria for acid and base. Here I have a very weak base, and I'm forming a very strong base. And obviously there are other factors here. You know, I'm forming a bond between the iodide and the carbon. Like, what does that count for, etc. But you don't even have to think about all that. You just never go from taking a really weak base to forming a really strong base, because you're going thermodynamically uphill in that situation. I have something that's not very reactive on the left side, on the reactant side. I just have a whole bunch of generally pretty stable species, and on the right side, I'm going to something that is very unstable, and we just don't see that. That's, again, just to use a macroscopic analogy, that's like if you saw, you're watching and there's a stone at the bottom of a hill and you just see it just kind of spontaneously move up the hill without anybody pushing it, just kind of goes up the hill. You'd be like, what the hell is going on? That's what this is the equivalent of. It's just, on the molecular level. So this doesn't happen. We can't do this. I'm just going to put I'm going to put an X through this. It didn't happen. Okay. But we can still do this reaction. I'm going to show you how. So if instead, though, we use hydroiodic acid, now I can do this reaction. And the reason is, and this is the mechanism for the reaction, in the first step what will happen is I'll pick up this proton. So remember when I said most of the stuff we do in organic chemistry involves some sort of acid-base chemistry. Hopefully you took that seriously, and now it's making sense why I stress that it's important to know those things. Okay, so now let's look at what we have. So if in the first step of the mechanism that happens, and we're saying that what was preventing the reaction from happening before, we weren't using hydroiodic acid, we were just using straight up iodide, we were saying that our leaving group was a bad leaving group. And that's because our leaving group, when it would come off, would form, if we look up here, we would form OH minus, which we know is a strong base. It's like a canonical strong base, right? But here, in this situation that we're at, now our leaving group is OH2. So what's our leaving group? Really, it's water, which we know is a very weak base. Now, this reaction can happen. Because our leaving group is a weak base, doesn't matter. Oops, I'm using hot pink for that one. It doesn't matter now. We're not going from weak base to strong base. We're going from weak base to, also weak base. So thermodynamically, it's not a big deal to do that. So one way to take an alcohol, which is generally not a good leaving group, is to add acid. And that doesn't work for all things, and I can give you some examples of that. But it works in these cases. So if you have a halogen that you want to do nucleophilic substitution with, you can add in some acid, and that'll protonate the alcohol group, and then you can displace the alcohol, which is now basically water, and get to your product. Okay. So if we wanted to go back to our leaving groups, let's say I'm going to scroll back up, I'm trying to do this slowly so I don't make you guys nothing. We could add in water as a good leaving group as well. Okay, and similarly, alcohols make good leaving groups. So if you come back down here and look at this, if you wanted to take the hydrogen here and swap it out for something else like a methyl group, you could still do this reaction, right? And then in the end, instead of having H2O, you would have something like CH3OH come off. I'm going to erase that because I think that's confusing. Okay, so protonating is one way to make it a good leaving group. That's for an SN2 reaction. Yeah, we can also do this in an SN1 reaction, doing just something very similar. So for example, if you wanted to do, let me think for a second. So let's say we're using, so the reason that this is SN2 and the reason that I know this is SN2 is because it's a primary substrate. And primary substrates only they'll never go through SN1. And we haven't quite gotten into that yet, but we're just kind of building up our tools here so we can discuss it in detail. So primary, as we know, but we do know that primaries are really fast for SN2, okay? And that tertiary favors SN1. So let's say, so now I'm going to put, I'm going to make this, let's say ethanol. How do I want to draw that? Trying to make it not confusing looking. Yeah, I don't know if that helps or hurts, but okay. So we've got ethoxide as our leaving group here. Okay. Yeah, if we try and do this SN1 reaction, like let's say you want to swap it out for something, like you put it in water and you want to do an SN1 where you want to switch that for water, this just never happens. You're not going to end up with this being the product that you see. And the reason for that, the reason that you don't see this coming in here, and I've done a proton transfer at the end there, But the reason that you don't see that coming in and doing that is because what would have to be our first step? This would just have to spontaneously come off to form this extremely high energy situation where I have both a carbocation and an extremely strong base and honestly a very good nucleophile in solution together. And that just doesn't happen. We just don't see that. Okay? But if we take this and let's say that we do the same reaction, but now I'm going to do water, and I'm going to add in a small amount, just a teeny amount, of H2SO4. Okay? So H2SO4 we know is going to dissociate, and really what we can represent that as in solution is just H3O+. So let's see what that, in this case, you will be able to get that. Okay, so you do in fact see water come in and displace this. Okay, let's look at the mechanism for that. So what do we think our first step's going to be? So yeah, so we're in water, we've got H2SO4, which means that what we really have is the hydronium ion. And so what's going to happen is those electrons are going to go and they're going to pull a proton off of hydronium. Okay, that protonates that. So now when we look at our leaving group, so before if it left, it would leave as ethoxide, which is basically as strong of a base as hydroxide. But now if it leaves, it just leaves as ethanol. And we know ethanol is a weak base. If you've ever had like a beer or any kind of liquor, you know, it's not caustic, it doesn't burn your throat. Well, it does, but not because it's basic. But yeah, so then what happens? And then remember, this is an SN1 reaction that we're drawing down here. So this is SN1. So we know that our first step is just going to be for this to pop off. And now we form our carbocation. And it's not as disconcerting because now we formed ethanol, not some super strong base. It's not this really, really high energy thing, although a carbocation itself is very high energy. We're just looking at the leaving group here. And then water can come in and attack that carbocation. Okay. And then we know that that's not what we want as our product. We've seen this before with some of our other reactions. What we do, we come in and water comes in and pulls that off. And then we get our product. And that is our mechanism. That there is our mechanism. So for both SN2 and SN1, sometimes you can get away with just adding a little bit of acid if you have a bad leaving group, and that'll allow you to kind of convert it over to a good leaving group, and you can still get your reaction to go. I'll show you in the next video. I'll try and make you aware of some situations where adding acid won't help you, and then we'll talk about a strategy around that. Okay. Ultimately, we're going to get to, is this SN1 or is this SN2? That's, that's a piece of this. We're trying to build up to that.